a limit like that, we are going to call it indeterminate quotient. Indeterminate is the word in here. Okay. Indeterminate quotient. Indeterminate quotient is the limit of a quotient in which the limit of the numerator is equal to 0. The limit of the denominator is also 0. Okay. In this case, we call it an indeterminate quotient of 0 to 0 type. I want to repeat. Okay. If the limit of the numerator is equal to 0, if the limit of the denominator is also 0, then we call the whole limit the indeterminate quotient of type 0 to 0. Some people also call it indeterminate form. It doesn't matter. We just call them indeterminate quotient. Okay. That's one type of the indeterminate quotient. The other type is infinity to infinity type. Okay. I guess you know the meaning now. Okay. It's the limit of a quotient in which the limit of the numerator is infinity, and also the limit of the denominator is infinity. The meaning of the definition is here. So basically, the numerator and the denominator approaches one of the infinities. When I talk about infinity, it includes the negative infinity. Okay, as x approaches a. So this is another type of the indeterminate quotient. We say it infinity to infinity. Okay. The L'Hopital's rule, I haven't told you the formula yet. The rule will apply to two cases. Both cases are called indeterminate quotient. We have two types, 0 to 0 type, infinity to infinity type. Okay. If we have an indeterminate quotient, then we have a formula to compute the limit of an indeterminate quotient. Okay. In many cases, it can be transformed to a very, very simple limit. Now look at the statement of the L'Hopital's rule. Okay. The statement of the L'Hopital's rule is on the screen. Actually, there's only one condition you need to verify. I'm going to show you how to do many questions. There are only one condition you need to verify. The connection is OR. Okay. You just need to verify one of the two conditions. So basically, you need to verify the limit is indeed an indeterminate quotient. Okay. Sorry, I forgot to put the fraction bar in here. So give me a little moment. I haven't set up properly yet. That's my fraction bar. Yeah, sorry about that. It's not very straight. Okay. That's a fraction bar. I don't know why. If I change to high contrast color on PDF, the fraction bars are gone. I really don't know why. Okay. Again, to use the formula, all we need is to verify one of the two conditions. So because the connection here is OR. Okay. So basically, you just need to convince yourself the limit on the left-hand side is an indeterminate quotient. The first one says it's an indeterminate quotient of type 0 to 0. The second condition says it's an indeterminate quotient of type infinity to infinity. Okay. If the condition is satisfied, then the given limit, the given indeterminate quotient, can be computed using a new limit. The new limit is obtained by differentiating the numerator and the denominator separately. It's not the quotient rule. Okay. You differentiate the numerator, you differentiate the denominator, and then you take the limit of, you take the new limit. If there's one other condition, but in many cases you do not check the other condition. Okay. The other condition is that the new limit is either a finite number or infinity. Again, we have two conditions. Okay, one condition is the given limit is an indeterminate quotient. Okay, the second condition is the new limit is a finite number or infinity. Okay, if that's the case, then we can use that formula to compute the limit. In many cases, many cases, the new limit is much simpler to compute. Okay. So just try to remember the conclusion right now. Okay. And then I'm going to use many questions to show you how to use the formulas. You'll see all the fraction bars on up. Okay. We'll go over question 1 first, probably. Okay. I don't need the design. We're going to compute that limit. Okay. As the limit of two polynomials. Okay. Now let's recall what we mean by the limit of two polynomials. What we mean by polynomials. On the numerator, you have a polynomial of degree 5. On the denominator, you have a polynomial of degree 7, right? Each polynomial has a degree. Okay. We're going to use the L'Hopital's rule to compute the limit. But before we use the formula, we have to verify the condition, right? In particular, we have to verify it's indeed an indeterminate quotient. Okay. Now, I'm going to give you two ways. The first way is longer, the second way is shorter. Okay. So maybe the solution. Now let's recall what we mean by an indeterminate quotient. We compute the limit of the top, we compute the limit of the bottom. Okay. We want to figure out the limit of the top. So basically, we compute the limit of the numerator. The limit as x approaches 1. We only compute the limit of the top, the numerator. Okay. The limit of x to the power 5. I'm going to copy the numerator. I hope I copied everything right. So did I copy everything right? I think I did. Okay. So anybody want to tell me the limit? The function is defined at 1. The function is continuous. When the function is elementary function defined at 1, to compute the limit, we can just plug in 1, right? We can just plug in the number. So anybody want to tell me the limit of the numerator? So please, you just plug in 1 and compute the value of the function. Is it 0? 1 minus 3 plus 2 plus 1 minus 1, right? I think it's 0, right?
0, sir.
It's 0, okay. So the limit of the numerator is equal to 0. And also we have to compute the limit of the denominator. We want to convince ourselves it's a indeterminate quotient. Okay. We compute the limit of the bottom. So the limit of the denominator, the limit as x approaches 1, the limit of the denominator is the limit of x to the power of 7 minus 4x plus 3. I believe it's 0, right? You plug
0,
1
sir.
into the function. You plug 1 into the function. Again, when computing the limit of an elementary function, to put it simply, it's a function that can be written using one formula. Okay, if the function is elementary, okay, it's defined at 1, and to get the limit, we just plug 1 into the function, right? So we have the limit of the bottom is also 0. What can you tell me now? The limit of the top is 0, the limit of the bottom is 0. So we have an indeterminate quotient, right? So we have an indeterminate quotient of type 0 to 0. Sorry, I'm going to open my chat from the other screen so I can type something. Okay, so the given limit is an indeterminate quotient. Probably you want to mention the type of a type 0 to 0. Okay. After verifying the condition, then we can try to use the L'Hopital's rule. I know there are two conditions. The second condition, the limit of after taking the derivative of the numerator and the denominator, the new limit is a finite number or infinity. But in many cases, you just verify the first condition. So because the second condition, you have to compute the new limit anyway, right? Now, I was trying to write a full stop by the L'Hopital's rule. Okay. Now remember how to write that. It's a French name. It's Hospital's rule. So do not say L Hospital's rule. It's L'Hopital's rule. Okay. Hospital's rule is no smoking. Wear a mask. L'Hopital's rule. L'Hopital. The spelling is hospital. Okay. But the L'Hopital's rule. Okay. The given limit. Can include this little one in here. The given limit can be computed by a new limit. The new limit is obtained by differentiating the numerator and the is 1. I'm going to write okay. I think all of you guys know what's going on. Using the L'Hopital's rule, we convert the given limit to a new limit, and now the numerator is computed by differentiating the numerator of the given limit. Okay. So anybody want to tell me the numerator? Yeah, that's where we need to use the power rule, right? I think all of you guys can remember this at least. We take the derivative of the numerator. I think we have 5x to the power 4, right? We use the power rule. You know what I mean by power rule if you forget this. Okay, so minus 12x x to the power of 3, right? And then plus 4. So watch me please. 4x, I think. You take the derivative of that term, you have 4x, and then plus 1, and also the derivative of the constant is 0. We do not have to include that. And for denominator, we have 7x to the power of 6. We use the power rule. We differentiate. We take the derivative of, I'm trying to say the term in different ways. Differentiate, it means taking the derivative, right? 7x to the power of 6 minus 4, right? Minus 4, I mean. So the given limit now is converted to a new limit. The new limit is calculated using the L'Hopital's rule. The new numerator is the derivative of the old numerator. Okay, the new denominator is the derivative of the old denominator. Now, what's the answer to the new limit? Is the given function defined at 1? The function is a rational function. By rational function, we mean the quotient of two polynomials, right? Is the given function defined at 1? You plug 1 in the denominator, I believe it's 3 is not equal to 0, right? Now for the new limit, we just plug in 1, and then we have the answer to the new limit. Okay. Anybody want to tell me the final answer? Final answer, please.
Minus 2 by 3.
I think the denominator is 3, and the top is minus
2.
Yeah, minus 2. So thank you so much. Okay. Okay, so that's the whole story of the L'Hopital's rule. the whole story of the L'Hopital. Okay. In many cases, I still don't want you to write too many things. For the condition, I just want you to use a notation to verify the condition. Now I'm going to I'm going to give you the solution of a new way. Okay, the new way is much shorter. In the future, you just use a new way. Okay. The new way, still you have to verify the condition. I want you to verify the condition honestly. So later on, I'm going to convince you if the condition is not true, then you cannot use the formula. The answer will not be right. Okay. Still, the first thing you do is to verify the given limit is indeed an indeterminate quotient. Okay. You compute the limit of the numerator. We have seen the limit of the top is equal to 0, right? You just use a notation like this to tell me you have verified the condition and the limit of the numerator is equal to 0. So do you know what I mean? And also at the bottom, you write something like this. The limit of the denominator is also 0, right? We have seen that. The limit is taken as x approaches 1. The same limit, of course. Okay. Use a notation like that to indicate you have verified the condition. So we have an indeterminate quotient. Okay. And then to show you have applied the L'Hopital's rule, you just write L in here. Okay. You just write L there to indicate you have applied the L'Hopital's rule. Okay. My notations are not universal. If you do the question anywhere else, you have to write the full solution. But these are my notations. Okay. If you do something like this, I see you have verified the given limit is an indeterminate quotient, actually of type 0 to 0. And then you apply the L'Hopital's rule. I know in next step you differentiate the numerator, you differentiate the denominator. Okay. And then lastly you plug in the number, you have a limit. Simple enough. So in the future you just show your work something like this. Okay. And also I forgot to mention the last limit is a finite number. So this is by that we mean the second condition is true. Okay. The second condition is the resulting limit after taking the derivative of the top and the bottom. The resulting limit is either a finite number or infinity. Okay. So that's the other condition you have to know. Okay. Any questions about this? Easy, right? So too easy, super easy.
Okay. Sorry, sir. So you said if it's infinite, it does not work.
If it's infinity, it will work. In some cases, the limit is not in infinity. In some cases, I do not want to make the thing too complicated. Okay. Or you just remember in most cases, so this will work. In some cases, if you want a little bit more story, so now let's say if you're trying to take the limit of sine of x as x, now let's say it goes to infinity. You know the graph is oscillating or something like that, right? So the limit of sine of x as x approaches infinity, this limit does not exist. If you see something like this, then the L'Hopital's rule may not work.
No, sir. What I meant is, like, instead of your answer being finite, like at the -2/3, what if that was infinity or whatever, like you said? Because our answer is infinite.
If that's infinity, it will also work. If the answer is infinity, then it will work. Okay, I will show you the conclusion here. Okay, in the conclusion, the other condition is if the limit on the right hand side, if the limit of that is either a finite number or infinity or negative infinity. In this case, the formula is true.
Okay, thank you.
Okay. Thank you. So that's a very good question, I think. Okay, so we did one question. Okay, it's probably time for you guys to try a very similar question. Okay, I will give you a similar question to try. So next time, try to open the PDF, please. Okay. A very, very similar question to try. Okay. Let's. For the people who in my Math 101 last semester, so people know I have started to use in-class quizzes, right? Now let's do that as an in-class quiz. Okay. So this one is an in-class quiz. For the two guys who are not with me last semester, for all the in-class quizzes, I'm going to create a folder on D2L. Okay. At the end of the class, you will submit the in-class quiz. Try that, please.
Isn't this one the same as number 1?
Yeah, you are right. Sorry, I think I copied the wrong question. I don't know why this. Yeah, this is not copied. Now it should be. That should go. Sorry, in-class quiz. I'm going to remove this. So that's a new one. Right? I have to draw a new bar, guys. Okay. Do that, please. That's an in-class quiz.
Mr. C? Number 1 and number 9 are the exact same question.
Still?
Yes.
It's weird.
Yeah, if you look on the PDF, it says that number 1 is the exact same one. And number 9 is the same as well.
Yeah, that's okay. Yeah, so that's okay. Sorry about that. I was trying to make up a new question. It's okay. Well, I think I copied the wrong thing, but that's it. It's okay. It's okay. It's okay.
Sounds good.
How about we do number 2? Okay, we do number 2. Try number 2, please. Number 2 is important. So do number 2, please. Okay. I will leave you alone for a little moment. Okay. Actually, for all of you guys, you need to recall the chain rule. Okay. To differentiate the numerator, you need to use the chain rule. Okay. As x goes to 0, the denominator goes to 0, of course, right? And also the numerator, you plug 0 into sine function. Okay. Into the numerator, the limit of the numerator is equal to sine of 0. Sine of 0 is equal to 0. So it's indeed a limit of type 0 to 0. So please do honestly verify that condition. And then you use a notation something like this to indicate we're applying the L'Hopital's rule. Okay. Again, I want to mention it's only my convention. If you do it on any other test, you probably have to mention the L'Hopital's rule or whatever. You're going to have a new limit. I have my chat open. So anybody want to tell me the derivative of the numerator? Yeah, probably I'm going to give you one more step. We differentiate the numerator, and then we differentiate the denominator. I have my chat open. So anybody want to write the limit of the derivative of the numerator? Yeah, that's correct. Yeah, that's correct. You do need to. I told you before, chain rule is everywhere. If you still have problem with chain rule, then you could be in trouble. Okay. I'm going to review this. Okay. To differentiate the numerator, we differentiate sine of 3x. Okay. To use the chain rule, you have to choose u, so that the given function as a function of u is simple to differentiate, right? And then you differentiate the function with respect to u. You differentiate sine of u. U is the whole thing in the box, right? You differentiate sine of u. You have cos of u. You have cos of u. You do not write u. You write u in terms of x. You have cos of u. I said u. I wrote 3x. Cos of the box, right? We are not done yet. Whenever the box is a function of x, you have to keep on going. You have to differentiate u. You have to differentiate the box. You have to differentiate 3x, right? So you end up with something like, I think Eugene said it right, 3 times cos of 3x. Okay. Now on the numerator you have 3 cos of 3x. Now can we plug in the number to get the limit? The given function is elementary, right? The given function can be written using one formula. The given function is defined as 0. You plug 0 in. Cos of 0. Cos of 0. You really do not need a calculator, do not need anything. You need to remember the value now. Okay. Cos of 0 is equal to 1. Okay. So the final answer is equal to 3. Right? Simple enough. Still, the in-class quiz I want you to submit. So we're done. We're done question 2. Okay. Now we move on to question 3. Okay. Now question 3 is kind of for question 3 you can think about question 3 a little bit. Okay. Again, the fraction bar is missing. I don't know why. If I change PDF to high contrast, all the fractions are gone. All the fraction bars are gone, I mean. I know some of you guys have tried, are trying at least. So, but there's a little trick. Okay. So maybe I'm going to go over this. Okay. The given limit is equal to. I'm going to do that in 2 steps. Okay. The given function can be written in something like. Now let's recall a basic property we learned in high school. Okay. We learned something like a over b the whole thing squared is equal to a squared over b squared. Actually, the property is true for any n exponent n. I mean, okay. We apply that property the other way around. I think the other way around. Okay. The given limit can be written as the limit of sine of 3x. You could try to use the L'Hopital's rule directly to verify it's an indeterminate quotient or something. Okay. So, but I'm going to use one other way. So the function, we take the limit of the function. The function is written as that function, the whole thing squared. You'll remember in Math 101, we learned a property of limit. If we take the limit of a function squared, the limit is actually the same thing as we switch the location of the brackets and the limit. That's a property we learned in Math 101. I'm pretty sure you can remember that. Okay. So basically, the limit of that is equal to the limit as x approaches 0, sine of x over x. Sorry, sine of 3x over x, the whole thing squared. Okay. Again, the first step I was trying to use that property. The second step I was using a property we learned in Math 101. Okay. Now the inside limit, inside the brackets, we have seen that limit in question 2, right? The answer to the limit inside the brackets is 3, right? So we use the answer to question 2. So maybe by question 2. By question 2, so the limit of that is equal to 3 squared. Now let's recall the limit inside the brackets in question 2 is equal to 3, right? We compute 3 squared, we have 9. On the assignment, you are going to have a question like that. If you see you are taking the limit of something to some power, try to use that property. In many cases, it's easier. Okay, that's my intention for question 3. Okay. Simple enough. Now let's move on to question 4. Okay. It's not an in-class quiz, but I want you to try it for a little while. Try it for a little while, please. Try it for a little while. So maybe I can go over something, okay? We verify the condition. It's the indeterminate quotient of types 0 to 0. And then we apply the L'Hopital's rule. We differentiate the numerator, we have 3x squared. We differentiate the denominator, we have 6x squared, right? 6x squared. So the answer is half. The answer is 1/2. The answer is 1/2. I was tricking you. So anybody want to? I want somebody to tell me I did something wrong. Is it wrong? Or what's wrong? Or what's wrong? What's wrong, please?
The denominator doesn't equal 0.
Yeah, the limit of the denominator is not equal to 0. Or you can say the given limit is not an indeterminate quotient, right? The given limit is not an indeterminate quotient. So this solution is wrong. I was trying to convince you it's essential, it's super important to verify the condition, to honestly verify the condition before you apply the formula, okay? Or otherwise the thing is wrong. Okay, now look at the right answer to this question. Okay, I think the given function is defined as 0. So what should be the right answer to the question? I think you plug 0 into the function. You have, I mean the function is elementary, right? It's defined as 0. To get the limit, you just plug 0 in, so you can get the limit, right? So the limit is equal to 0. You see the answer is different. Again, you have to verify the condition honestly before you can apply the L'Hopital's rule, okay? Or otherwise, the answer is wrong. So does that make sense? That's my intention. Okay, now I want to move on to question 10. I will move on to question 10. Okay. I told you earlier, indeterminate quotient has two types. One type is 0 to 0. So by that we mean the limit of the numerator is equal to 0. The limit of the denominator is also 0. So that's the indeterminate quotient of type 0 to 0. Actually, there's one other type. Okay. Represented by that question, we're talking about the other type. As x approaches infinity, what is the limit of the... Now let's talk about the numerator first. Okay. What is the limit of the numerator as x approaches infinity? Yeah, to see that, probably the a easier way. I'll try to see an easier way. Actually, the limit of the numerator is negative infinity. If you see what's going on, I will see if I can convince you a little better. So how about? So do not copy yet. I'm going to try if we can see that a little bit better. Okay. We take out. So now let's say negative 2x cubed, and then we have I think we have positive 1, and then plus 1 over. I think this will work. This will work. I mean, okay. I think 1 over x. And probably you have a negative 2 on numerator. So do you see as x gets larger and larger positive, this factor gets larger and larger negative? That factor gets closer and closer to 1. So because negative 2 over x approaches 0, right? As x approaches infinity. So the answer is negative infinity. I'm trying to say the limit of the numerator is negative infinity. The limit of the denominator is infinity. The limit of the numerator is negative, so negative infinity. You use a notation like that to tell me the limit of the numerator is negative infinity. The limit of the denominator is actually infinity, right? As x gets larger and larger positive, e to the power of x gets larger and larger positive as well. Actually, it's getting larger and larger positive much faster than x. Okay. Now let's recall the graph of exponential function. I think it's something like this, right? As x gets larger and larger positive, e to the power of x gets larger and larger positive faster. In any case, the limit of the denominator is also infinity. Okay. Again, use notations like this to indicate you have verified the condition. Okay. So it's also an indeterminate quotient. I'll go back to the. It's an indeterminate quotient of the second type. Okay. It's indeterminate quotient of type infinity to infinity. You see the limit of the numerator can be infinity, can be a negative infinity. The condition is satisfied, right? We say it's the indeterminate quotient of type infinity to infinity. Okay. Right. Okay. The condition is satisfied, right? And then we can apply L'Hopital's rule. Well, And then we differentiate the numerator and the denominator. So we have e, the derivative of e to the power of x is e to the power of x, right? Probably you want to open your Math 101 textbook to get all the basic formulas. Probably you need the basic formulas. At this time, you really, yeah, I'm talking about the two guys who took my calculus years ago, last year, I think both of them are two guys. So did the course last year. Okay, now the power rule. The derivative of the numerator, you have 6x squared, negative 6x squared, then plus 2x. So watch me please. Okay. I forgot something important, okay? So do not forget the limit notation. For some reason, I forgot that, okay? I know that's a common mistake, so do not forget that. Anybody want to tell me what to do next? This limit still is hard to compute. This limit is still hard to compute. Actually, for this question, I have two intentions. One intention is that I want to show you at least one limit of type infinity to infinity. Actually, I have one other intention. The other intention is yeah.
So we have to split the limit like 0 to something and something to infinity.
It's also infinity to infinity. I'm trying to say, yeah, I think you got
Okay,
it.
sir.
I'm trying to say you need to apply the L'Hopital's rule one more time or many more times. Again, my second intention is to show you a question that you need to apply the L'Hopital's rule many times. Okay, probably for this one you need to apply the rule a few more times. Okay, you can see the pattern. You apply the L'Hopital's rule one time, you reduce the power by one, right? I mean, you reduce the degree. You reduce the degree of the polynomial by one. Okay, the denominator is not changed. If you keep on going, eventually the derivative of the numerator is going to be a constant, and then you're going to get a limit. Okay, does that make sense? I will just keep on going. Okay, the limit of the denominator is infinity. It's infinity again. The limit of the numerator is negative infinity again, right? Sorry about my handwriting. Negative infinity. Okay, so it's so we're ready to apply the L'Hopital's rule the second time. It's because it's still an indeterminate quotient, right? Now we differentiate again. So as x goes to b, and the derivative of the denominator is the same, e to the power of x, right? Now the derivative of the numerator is negative 12, I think x, and then plus 2, is that right? I think I got it right. Okay. Indeterminate quotient again. Indeterminate quotient of type. And we do not say this is indeterminate quotient of type negative infinity to infinity. We still say it's type infinity to infinity. Okay. When I'm trying to say, when verifying the condition, it's permissible for the infinity to be one of the numerator or the denominator to be negative infinity. Okay. I think it's a little bit messy in here, but I hope you know what's going on. You are going to be excited after we apply the L'Hopital's rule one more time. Okay. This limit is still of type infinity to infinity, and then we apply the L'Hopital's rule one more time, and then we can have the answer. Okay. The derivative of the denominator is equal to e to the power of x. The derivative of the numerator, I believe now, is negative 12. Now, anybody want to tell me the final answer now?
Negative 12 over infinity.
Negative 12 over infinity. We do not say that. The final answer is 0. Final answer is 0. You just imagine as x gets larger and larger positive, and then negative 12 over huge positive number is a very tiny number. So this means the limit of the function is equal to 0. Okay, again, my intention on that question, I have two intentions. One intention is to show you a limit of type infinity to infinity. The second intention is, in some cases, you need to apply the L'Hopital's rule more than once. From the many questions we just did, you can see what I'm trying to say. You can see the L'Hopital's rule is super efficient. Actually, in the future, is super useful. Even for a simple question like question 2, using the knowledge in Math 101, it could be you could be doing many other things. Now let's go back to question 1. Now let's recall for question 1, when computing that limit, if the numerator and the denominator are both polynomials, without the L'Hopital's rule, you have to factor the numerator and the denominator. You want to cancel out x minus 1 or something, but for a polynomial of higher degrees, it's probably a little bit hard to factor even, right? So you can see how powerful the L'Hopital's rule is. Okay, so the next question I want to go over is number 6. Okay. In question 6, you do not see a quotient. Actually, if you look at the textbook, sorry, I forgot to mention the textbook. Actually, the textbook is the same as the textbook in Math 101. We have a textbook. Okay, it's an open textbook. It's the link is on the syllabus. If you look at the textbook or any textbook, they summarize many other indeterminate forms. But I really do not want you to memorize too many forms. Okay, you just remember the L'Hopital's rule can only be applied to an indeterminate quotient. For any other form, you need to convert the limit to a limit of a quotient. Okay. Questions. So number 6 is designed for that purpose. Okay. You don't see a quotient, right? So the first thing you do is to convert the limit to the limit of a quotient. In particular, you want to convert the limit to an indeterminate quotient. Okay. Okay. Now, how to do the conversion? And so basically, the idea is to rewrite the limit to the limit of a quotient. Okay, first. In some cases, there's more than one way to convert the limit to a quotient. So maybe some ways will not work, but some way will work. You don't have to get the thing right at the first time. You can try. Okay. Now let's try something first. Okay. Now the limit as x approaches infinity. Okay. We want to convert the limit to the limit of a quotient. Okay. We take out a common factor first. Okay. We take out a common factor of x first, right? And then e to the power of 1 over x minus 1. All of you guys know what's going on here. Okay. Okay, now a quotient. We want to convert the thing to a quotient. How do we convert the thing to a quotient? As the limit as x goes to infinity, I will try to ask you some question. Okay, if I leave the stuff, the function in the brackets on the numerator, what would be the denominator if we convert the function to a quotient? So just tell me what should be the denominator here. Here you have x.
Or 1 by x?
Yeah, 1 by x, 1 over x is the same thing. Okay. If you have trouble with this, you could be in trouble. You just try to divide the two fractions. You are going to return this to this. Okay. I think all of you guys know what's going on here. So just a little conversion. Okay. Okay. Again, for that function, there might be two ways to convert the function to a quotient, but one way will work. Actually, that way will work. Okay. Now, the next step, we are going to verify the condition. We are going to verify the limit of this quotient is indeed an indeterminate quotient. Later on, I'm going to tell you why we call it an indeterminate quotient. What we mean by indeterminate. Okay. Actually, for indeterminate quotient, the answer can be a finite number, can be infinity, can also not exist, can also be 0. Okay, that's why we call it indeterminate. Okay. So very shortly, I'm going to make more comments. But now we'll move on to verify this limit is indeed an indeterminate quotient. I'm going to use my notation. Okay, again, it's only my convention. Okay, as x approaches infinity, what is the limit of the denominator? As x goes to infinity, what is the limit of 1 over x? As x gets larger and larger positive, 1 over x approaches 0, right? So 0 is the limit of the denominator. Okay. You just imagine as x gets larger and larger positive, 1 gets tinier and tinier. Okay. The next thing you have to verify honestly, as x gets larger and larger positive, what is the limit of the numerator? As x approaches infinity, what's the limit of the numerator? Now follow me, okay? As x approaches infinity, as x gets larger and larger positive, 1 over x gets closer and closer to 0, tinier and tinier. By tinier, I mean very close to 0, okay? And then e to the power of x gets closer and closer to 1, because e to the power of 0 is equal to 1, so that makes sense? And then 1 minus 1 is equal to 0. I'm trying to say as x gets larger and larger positive, e to the power of 1 over x minus 1 gets closer and closer to 0, which means the limit of the numerator is equal to 0. You use a notation like that to indicate the limit of the numerator is equal to 0. Again, that's only my conversion. Okay. I mean the notation. Okay. If you do it anywhere else, you need to verify the conditions by writing some words. Okay. So we are ready to apply the L'Hopital's rule. Okay. The condition is satisfied. Now we are going to apply the L'Hopital's rule. Okay. The limit as x approaches infinity. And then we differentiate the numerator and the denominator. Okay. I told you to memorize the derivative of the denominator of 1 over x before. I told you to memorize because we are using it over and over again. The derivative of the denominator of 1 over x is negative 1 over x squared. I told you to memorize before, right? And then the derivative of the numerator, because it's the first Math 102 class, I need to review something from Math 101. The derivative of the numerator, you need to differentiate e to the power of 1 over x, right? You see chain rule in here again. You have to use the chain rule, okay? You choose 1 over x as u. You differentiate e to the power of u first. E to the power of u. E to the power of u is e to the power of u, e to the power of 1 over x. Inside u, I wrote 1 over x, followed by the derivative of u, because we are using chain rule, right? The derivative of u is negative 1 over x squared. I'm 100% sure this derivative is one of the questions we did in Math 101. I told you that in most cases my first question to ask you to do in Math 102, but I forgot to ask you to do that in this time. Okay, taking the derivative of the numerator, we have e to the power of 1 over x, and then times, I'm copying from here, now look at my cursor, okay, and then times negative 1 over x squared. Simplify, now simplify, okay. Why can we cancel out that factor? As x approaches infinity, this factor is a non-zero number, right? Approaches infinity, it means x gets larger and larger. In any case, that factor is a non-zero number. That factor is not equal to 0, I mean, okay. That's why we can cancel out a non-zero factor. So I think I have enough room to finish this. So we end up with the limit as x approaches infinity, limit of that. The function is e to the power of 1 over x. We end up with that limit. Okay. For this one, we do not have to use any L'Hopital's rule or whatever rule again. Anybody want to tell me the limit? Limit of this? I mentioned earlier. Okay. As x gets larger and larger positive, 1 over x gets tinier and tinier, gets closer and closer to 0. And the e to the power of something getting closer and closer to 0 is e to the power of 0, right? E to the power of 0
is 1.
Is 1, okay.
Yeah.
It's 1. Good. Okay, it's 1. Good. Represented by number 6. In some cases, you need to convert the limit to the limit of a quotient before you verify the condition. Okay, so that's my intention on this. But still, in any case, you need to, in particular, if you forget about chain rule, you need to review the chain rule seriously. So get your Math 101 notes, review the chain rule. We spent a long time on chain rule. Okay. So we did number 6, I think. Yeah, probably I'm going to leave number 5 as one of your quiz question you do later. Okay. For number 5, I'm not going to do a complete solution. Okay. So we do it later. Okay. Now I'm going to move on to 7. Okay. Only if you look at the textbook or any other textbook, so people might call the limit in question 6 indeterminate form of type infinity minus infinity. So don't worry too much about that. Okay. You just remember in many cases you need to convert the function to the limit of a quotient, so that it's an indeterminate quotient, so that you can use the L'Hopital's rule. Okay, now we're going to do 7. Okay. In 7, we're trying to get the limit of, you see the form of the function as one function to the power of another function. In this case, the natural log will work good. Okay, I will tell you the trick. I will show you the complete solution to this one. Okay. Again, the following trick will apply to the case when we are taking the limit of one function to the power of another function. I will give you a complete solution to that. The solution could be a little bit long. I'll try to divide the screen into 2 halves to see how it works. Okay. We're going to take natural log. Okay. But before that, we the solution. I want to use y to denote the given function. Okay, the limit of the function. I want to use y to denote the function. We let y be the function. The given function is 1 plus 3x, and then to the power of negative 1 over 2x. We use a notation to represent the function. We use y to represent the function. Okay, you're going to see why I want to do that later. And then I want to take natural log of y. Okay. Again, for all the limits in the form of one function to the power of another function, you use the following technique. Use y to denote the given function. Okay. And then we take natural log of y. Okay. We take natural log of y. Okay. Okay, I'm going to do that in 2 steps. Okay, we take natural log of y. So by that we mean we take natural log of 1 plus 3x and then to the power of negative 1 over 2x. Okay. The whole thing of that is on exponent. So do you want to recall one property we mentioned before? So natural log of a to the power of b is converted to b times so natural log of a, right? We use that property over and over again. In Mat 1.1, we learned logarithmic differentiation. Remember that? Okay. So which means so natural log of y is equal to negative 1 over 2x, and then times natural log of 1 plus 3x. Okay. I'm going to write that in terms of a quotient. Now it's easy, right? In terms of quotient, so natural log of y is equal to, in terms of a quotient, yeah, probably I want to leave the negative sign on denominator. It doesn't matter you leave it on denominator or numerator. Okay. On denominator you have negative 2x in here. I believe on numerator you have natural log of x. Okay. Taking natural log of y. Okay. Taking natural log of the given function, you are going to, and then convert the whole thing to the form of a quotient. Okay. The next thing you do is to take the limit of natural log of y. Okay. The limit of. I'm going to start from here. I hope I have enough room. Okay. And then we compute the limit of natural log of y. Okay. Maybe I'm going to use brackets here. Okay. The limit of natural log of y is actually the limit as x approaches 0. The limit as x approaches 0 of, on denominator you have negative 2x, on numerator you have natural log of 1 plus 3x, right? So you end up with the limit of a quotient, right? At this point, we are trying to use the L'Hopital's rule. So, but before that, we need to verify the condition. We need to verify as the limit as x goes to 0, the limit of the numerator and the limit of the denominator are zeros, right? Or infinities, or one of the infinities. Okay, now look at the denominator first. As x goes to 0, the denominator negative 2x, I believe the limit of the denominator is equal to 0. Okay, my convention is to use that notation to indicate the limit of the denominator is equal to 0. How about the limit of the numerator? The limit, the numerator is, look at only the numerator. Okay, so defined as 0, right? The numerator is defined as 0. Yeah, the limit of the, I'm trying to tell you why. Okay, the numerator is elementary function, so defined as 0. You plug 0 in, you have the answer natural log of 1. Natural log of 1 is equal to 0, right? So the limit of the numerator is also 0. Okay. So we do have a indeterminate quotient of type 0 to 0. Verify the condition. Okay, the condition for the L'Hopital's rule. After that, we apply the formula. We apply the L'Hopital's rule. Okay, we take the derivative of the numerator, the derivative of the denominator. Okay, the derivative of the denominator, I believe, is negative 2. Okay, the derivative of the numerator. So please, I want you to try the derivative of the numerator for a little while. Okay, we need to use the chain rule. That's a. I will give you 2 minutes. Okay. So please write your answer on the chat. I want to make sure you know how to differentiate that. Okay. Yeah, that's good. Yeah, that's good. Yeah, that's super good. Okay, I think now for the numerator, it's so can I write a line in here? I know it's a little messy, or otherwise it could be confused. I think the derivative of the numerator, you are going to get 3 over 1 plus 3x, right? That's right. Yeah, that's good. That's good. Okay. After applying the L'Hopital's rule, we end up with a limit like this, so which is super easy. Now the final answer, please. I think the final answer, the given function, the function is defined at 0. Okay, you plug 0 in. I think you're going to have the answer to the limit. So the answer to the limit is negative 3 over 2. Is that right? You plug 0 in, you have the answer. Right? We are not done yet. So that's only the limit of natural log of y, right? If you look at the beginning, where we were trying to compute the limit of natural log of y. If the limit of natural log of y is equal to a number, how can we get the limit of y? So the given limit, now look at 7, okay? We set y to be the given function. We are trying to compute the limit of y, right? So the given limit is the limit of y as x approaches 0, I believe. The limit of y. Okay. What is the relation between y and the natural log of y? It's not too long story, but I think I do not have too much time to review this. I'm going to review an identity you learned in high school. Okay, y is always the same as. Now we're going to make a connection between y and natural log of y. Y is always the same thing as e to the power of natural log of y. Okay. So just remember the identity. Okay, that's a identity you learned in high school, in calculus 12. Okay, now we are going to make use of that. Strictly speaking, we need to use the property that e exponential function is continuous. Okay, we take the limit of y. It means we are taking the limit of e to the power of y. Sorry, e to the power of natural log of y. Okay, I think it's not too messy here. As x goes to 0. Okay. Strictly speaking, by the continuity of exponential function, so but you can just use this without knowing too much of the y side. Okay. The continuity of e to the power exponential function ensures you can put the limit at this location. You just use the identity. Okay. So this limit is actually the same thing as e to the power of the limit as x approaches 0 of natural log of y. Which is, we have seen the limit of natural log of y, okay, is equal to e to the power of negative 3 over 2, right? So because this part, exponent part, is negative 3 over 2. Okay. Okay, I'm going to summarize a little bit. Okay, this type of the limit is considered as a little bit hard. Okay, so basically, when you see the limit is in the form of one function to the power of another function, you use the following technique. Okay, so first of all, you set y to be the given function, one function to the power of another function. Okay, and then you take natural log of y. Using the property of natural log or any log, you can convert the function natural log of y to the form of a quotient. The next thing you do is to take the limit of natural log of y, which means we are taking the limit of a quotient. You need to verify it's indeed an indeterminate quotient before applying the L'Hopital's rule. Okay. In many cases, after applying the L'Hopital's rule, you are going to get a finite number. Now, also remember the last step. This number is not the limit of the given function. This is the limit of natural log of y. We are trying to get the limit of y. You use that property. You use that identity. That's a identity, which means that equation is always true. Okay. You use that identity to get the answer to the limit of y. Okay. That is the whole story. So put that in the notes. Okay.